All right, 7.4, equations with rational expressions. So, as you've noticed, most of our chapters start off with expressions, right? The things that don't have equal signs, and we learn how to reduce them, right? And then we jump into the equations. We did that last time with factoring polynomials. We started off with all these things, ways you could multiply and add and factor, and then we started solving with zero product property. We're going to do the same thing now with rational equations. So a rational equation takes rational expressions and it puts them together with an equal sign. They don't need to all three have be rational expressions. Most of the time you will see that, and that's usually the ones we will be solving because those are the most, those are the most detailed ones. But you can have things like 3x plus 5 equals 9. That is also a rational expression, a rational equation, because it's got at least one rational expression. But again, those are pretty boring, so we're not going to do those. We're just going to do the ones that have multiple rational expressions. So let's take a look at this one. 2 over x minus 3 halves minus 7 over 2x. Now, clearly this is a combination of 3 different rational expressions, right? You've got 2 over x, 3 halves, and 7 over 2x, right? 3 fractions. Because it's all fractions, we have to worry about the domain. Remember way back when in section 7.1, we were talking about the domain, because it's very important not to have these bottom guys equal 0, right? None of those guys can equal 0. If they do, it doesn't make sense anymore. So if any of our x's were to equal 0, that would be a problem. So let's see if we can find the domain of these following rational equations. What would be the domain of the whole equation? Well, it's going to be the intersection of all 3 domains. So let's look at these as 3 separate entities. 7 over 2x. Okay, so we've got this first guy, 2 over x. What is the domain here? Well, x cannot be 0, so the domain is everything such that x does not equal 0, right? So the domain is everything it can be. We want to say it's x, all the x's in the world, except 0, right? So that's cool. That one's pretty easy because the whole denominator was x. I didn't have to worry about it being some other value that would end up equaling x, right? Or end up equaling 0. The second one is just a number, therefore it has no domain. There is no x, right? There's no x to worry about, so we don't need to worry about that one. The last one, just take a breath. What would make this denominator equal to 0? Well, I can solve that. If 2x equals 0, divide by 2, it looks like the only x that's going to make that happen is 0. So this is also the domain x such that x does not equal 0. And so we have the 2 potential domains here. The domain of the whole equation is just going to be, both of these guys combined together. Since they're exactly the same, our whole domain is x such that x does not equal 0. In other words, we can plug in anything we want to except 0, because otherwise it would fail on both the first term and the last term. Alright, let's do it again with this one down here. Same idea. We can't have any of those denominators equaling 0. But now the difference is in where the first problem, the entire denominator was x. This time, x minus 3 is a denominator, right? It's not just x. So we have to figure out in each case what is not allowed. So for this to equal 0, if this equals 0, sorry, just wanted to erase that. Then if this bottom equaled 0, then that means x would have to be what? For x minus 3 to equal 0, add 3 to both sides. And I find that x cannot be 3, right? So in order for that to happen, x cannot be 3. So this first domain would be x such that x does not equal 3. Alrighty, this second domain over here, let's take a look at the second term. So minus let's do orange. 3 over x plus 3, right? So what would cause it to fail in this case? That would be, okay, x plus 3 would equal 0. What plus 3 equals 0? X cannot be negative 3, right? X cannot be negative 3. So this domain would be x such that x does not equal negative 3. And then we do the last one, 12 over, stop choosing red. Okay, 12 over x squared minus 9. In order for that one to fail, then the bottom here would have to equal 0. Well, x squared minus 9 cannot equal 0. I notice that that's a special case, right? So I can factor that into x plus 3x minus 3 equals 0. Zero product property says x plus 3 cannot equal 0. And x minus 3 cannot equal 0. Because otherwise, either way, if either one of those was true, then one of these would be 0, right? So then the whole thing would be 0. So x cannot be negative 3, and x cannot be 3. So the domain for this last guy is x such that x does not equal 3 or negative 3. And then the domain for the whole equation is just going to be the combination of these three colors here. So the whole domain would be x such that x does not equal negative 3 or 3. In this case, whoops, that's a horrible 3, sorry. Or 3. In this case, the purple one ends up being the same thing. That's just a coincidence. But it just combines all three together to get us a whole domain of what they can't be, right? So it's very important to remember that. Alrighty. Hopefully that domain was just a quick reminder of the domain and what x can and cannot be. It's majorly important now that we're actually solving these. Up until now, we've just been reducing them, right? We didn't have to worry about plugging in stuff for x. But now we're actually getting answers. If it happens that the answer we get, like let's say, so this same equation is down below in solving. Let's say for this answer, we end up getting x equals 0. That's a problem because we know that x cannot equal 0, and that happens sometimes. It's called an extraneous solution, and it just means that this equation has no answer. Okay, so we cannot, even if we do achieve an actual x equals 0, even if mathematically it makes sense, right? Then even so, it still violates the domain, and so this equation wouldn't work because we'd have to go plug it back in, and we'd get 2 over 0, and the universe would explode. So that's what we call an extraneous solution, and we're going to watch out for those. But let's go ahead and solve this first one. So it's the same equation we saw in the first problem. 2 over x minus 3 halves equals 7 over 2x. Excuse me. Okay. Here's what I'm going to do. I'm going to treat this like an addition-subtraction problem of all 3 terms. That's what I'm going to do. It's addition and subtraction for all 3 terms, okay? So I want to get all 3 to be the same denominator. You're going to see why in a sec. So I'm going to get all 3 to be the same denominator. So I'll start with an LCM. LCM of, let's see, what do they have in common? This one has an x. This one has a 2, so we've got an x so far, and a 2. And then here, that one is 2x, so it has both the pieces, so it looks like my LCM is 2x. Sweet, 2x. Alright, now I'm going to change each one of these so that they all say 2x. So from the first term, 2 over x, what's missing is the 2 part. So I'll multiply 2 times 2, right? That gets me 4 over 2x, right? 4 over 2x. Sweet. Let's do the second part. I have the next term, a minus 3 halves. What part's missing from my LCM? Well, I have the 2 part. I'm missing the x part. In order to multiply by an x on the bottom, I got to do it on the top. I end up with a minus 3x over 2x. Fabulous. The last one, 7 over 2x, right? It's equal to 7 over 2x. What's missing? Awesomely, a nothing. So 7 over 2x, it remains. And I have this new equation, right? Everything is the same on the bottom. Red, yellow, yeah, red, yellow, red. Over here on the left-hand side, since I have 2 fractions of the same denominator, I can combine them to 4 minus 3x over just a 2x, right? Combine them. That still equals a 7 over 2x. Okay, so now I've only got one thing on each side. That's cool, and they both have the same denominator. Here's the reason I wanted to do that. What I'm going to do now is on this left-hand side, I want to get rid of the denominator. I want to take it out. In order to do that, I can multiply by a 2x to this side. Remember your properties of equality? It says you can multiply anything you want to one side as long as you do it to the other. Before now, we didn't have an equal sign, so we couldn't do that. Now we can. So if I multiply a 2x over here, I can cancel those 2 guys, thanks to the equal sign. And all I'm left with is a 4 minus 3x. The best part, though, is because the other side matches, when I multiply it over here, that also cancels, and I'm just left with a 7. So by making sure these two things match, by making sure these two guys match, I can actually cut them both out by multiplying on that to both sides. And I'm just left with a linear equation. 4 minus 3x equals 7 is very easy to solve. Start as far away from the variable as you can. You get negative 3x equals 3, or x equals negative 1. Okay? So that's how I arrive at a solution. Right? So the idea was put everything over the same LCD so that they go away and you're left with something nice and easy to solve. But before I go boxing this answer, I'm going to remember what I just said about the domain. The domain says that if I plug this in, I'm not going to get 0 on any bottoms here. Well, we decided earlier that the domain was everything except 0. Since negative 1 is not 0, it's not going to be a problem here. And I can double check that real fast. I get 2 over negative 1 minus 3 halves equals 2 over 2 times negative 1. Yep, none of that's going to be 0. So I end up getting x is equal to 1/2. Oh, sorry, negative 1. And that's how you solve an rational equation. Let's try something. Let's try the same problem. The other problem we did the domain for. Let's try something a little bit more complicated. Alright, so this time I have 2 over x minus 3 minus 3 over x plus 3 equals 12 over x squared minus 9, right? Not as, pretty as just having an x in the denominator, but it's the same idea, Let's start with that LCM. Just going to kind of cut that off here. Start with that LCM. So I have LCM. Well, the first one has an x minus 3, so I know I'm at least going to need that. The second one has an x plus 3. Remember, that's not the same thing. So this is an entirely different x plus 3. And then if I look closely at this last one, that's going to be the same thing as 12 over x plus 3x minus 3 when I factor. So yes, you still have to factor it, right? Still LCM. I'm going to treat it like addition multiplication. So factor that out, and it looks like I have both pieces of those already. So that's awesome. Alright, so that's my LCM, right? That's my LCM. X minus 3 times x plus 3. Now I'm going to multiply that to each of my sides, or each of my terms, so that they are all the same denominator. So let's go ahead and do that now. Let's multiply, let's do orange. So this first term was 2 over x minus 3. I'm going to write it a little smaller. Sorry, I have to erase that. So I'm just going to go up and write it a little smaller. 2 over x minus 3. What's missing from that denominator? The x plus 3 part. So I'm going to multiply by what's missing, x plus 3. What I do to the bottom, I must do to the top. Multiply by x plus 3. Alright, and I end up getting 2x plus 6, right, when you multiply that out, 2x plus 6 over x minus 3x plus 3. And I'm not multiplying this one out because I want to end up canceling anyways, right? Okay, second term. I have, so this is another minus problem. 3 over x plus 3. What's missing from this one? The x minus 3 part, right? X minus 3, x minus 3. And I end up getting, so subtraction of, again, the numerator is just going to, the denominator is going to be the same. That was the whole point, right? Making the denominator the same. But the numerator is 3 times x and 3 times negative 3, so 3x minus 9. I'm putting it in parentheses because I know I'm going to be subtracting later, and I want to make sure I distribute that negative. Alright, the last one, the last term on the other side was equal to 12x squared minus 9, and as we saw, that's the same thing as the LCM, so that doesn't need to be multiplied to anything, and so that's equal to 12 over, if I factor it, x plus 3, x minus 3. Alright, and I have a new, larger, but more sustainable equation. Now I can take all of this and I can put it over one fraction. I'm actually going to go up here. Yeah, I'll put it up here. So I have 2x plus 6 minus, and I'm going to distribute that negative. So minus 3 plus 9 over x minus 3, x plus 3 is equal to 12 over x minus 3, x plus 3. So I've just combined these two tops up here, right? And then I think I'm going to combine the tops a little bit. Yeah, I'm just going to combine the tops a little bit. So I end up getting 2x minus 3x is a minus x. 6 plus 9 is a plus 15. And the other side we still have a 12. This side still over x minus 3, x plus 3. Over x minus 3, x plus 3. So all I did was combine this numerator here, combine this numerator into negative x plus 15. Now I'm going to do the fancy step. The reason we wanted the denominators the same, because then I can multiply it. X plus 3, x minus 3 to both sides. X plus 3, 3, and x minus 3 to both sides. They cancel, 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 right? And so I'm just left with the numerators. Negative x plus 15 is equal to 12. Negative x is equal to negative 3. X is equal to 3. Fabulous. But before I go boxing my answer, so we arrived at a solution, right? We got a solution. The only problem is, think of our solution and think of our domain. If we take that back and we plug that in, that's going to be a problem, right? 3 minus 3 in that first term, that's going to give us a 0 in the denominator. So this is an extraneous solution. Extraneous solution. And that is a problem. Cannot have an extraneous solution. So really, this equation has no solution. No solution. That's just how it goes. That's just how it goes. The only one that would have made sense there is 3, and 3 violates our domain. So it just doesn't have an answer. It's a no solution problem. So you always want to check those domains. Always want to check that domain. You don't need to go through and find the domain first, but just take your answer and double check it in the problem. If you get something that ends up giving you a 0 somewhere, then you have a problem, right? You have a problem. You double check your math first, make sure you didn't make a computation error, but sometimes you end up with an extraneous solution. Alrighty, let's try another one. We've got 3 more. So I've got I got 3 over p squared plus p minus 2 minus 1 over p squared minus 1 equals 7 over p squared plus 3p plus 2. As it is, definitely can't work with this, right? Can't even find an LCM until it's factored. So let's factor first. Start with p squared plus 2p minus 2. Oh, I'm sorry, not 2p, p. P squared plus p minus 2. So two things that would multiply to negative 2 and add to positive 1. That sounds like 2 and 1, where it's 2 and negative 1, right? So this guy is going to factor to p plus 2, p minus 1. Alright. Second guy, p squared minus 1, that's a special case. So I end up with a p squared minus 1, special case, p plus 1, p minus 1. And then the last one, p squared plus 3p plus 2, that's going to factor, let's see, two things that multiply to 2 and add to 3, p plus 2 and p plus 1. Again, if any of those were ambiguous to you, you need to go back to 6.2 and 6.3, look up factoring trinomials and special cases, then it'll make more sense. Okay. Now I can look at the combination between the two, or all 3 of them. So what would be my LCM here? My LCM is going to be, well, I have to start off with a p plus 2 and a p minus 1. Right? So Next guy, I already have a p minus 1 in the blue, so I don't need to add it again, but I don't have a p plus 1. And then this last one, p plus 2, p plus 1, I have both of those. So there's my LCM. One of each, right? One of each. Alright, let's take my original equation now and rewrite it using the factored form and with what's missing. So my first term, let me stick to the same colors. I had 3 over, and when I factored it, p plus 2 and p minus 1. There, so that's what it would be in factored form, right? That's the whole term in factored form. What's missing is that p plus 1, right? So I multiply it by a p plus 1 over p plus 1. My second term is going to be minus, I think it's minus, yep, 1 over p, second term was 1 over p plus 1, p minus 1. And what's missing there is the p plus 2, so we'll do p plus 2 over p plus 2. And that is equal to a 7 over p, let's see, p plus 2, p plus 1, was it that factored down to? What's missing would be the p minus 1 over p minus 1, p minus 1. Okie dokie. So lots to do there. So I'm going to combine these two guys together from the get-go. I'm going to do it down here. So I have 3 times p plus 1 minus p plus 2 all over p plus 2, p plus 1, p minus 1. And that is equal to, now since the other side was also missing a factor, I still have to multiply. So the other side's not always going to be equal, but I'm going to check the other side too. So I have 7 times p minus 1 over p plus 2, p plus 1, p minus 1, right? I can multiply by the denominators on both sides. That ends up canceling, right? And I end up with, sorry, my stylus is kind of large, so I'm going to go over here. I end up with 3p plus, sorry, so 3p times 1 minus p plus 2 is equal to 7 times p minus 1. Those are the numerators after I dealt with the denominators. And this is just a simple distribution problem. Distribute these guys, I get 3p plus 3 minus p minus 2 equals 7p minus 7. Let's see, so 3p minus p would be 2p plus 1 is equal to 7p minus 7. Subtract 2p, you get 5p over here. Oops. So 5p. Add 7 is equal to 8. P is equal to 8/5. P is equal to 8/5. Alright, we'll double check that that's not a problem. So I can't have, let's see, I can't have this one be 0, this one be 0, or 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 this one be 0. So it looks like I can't have -2, +1, -1, +1, -2, -1. So I can't have -2, -1, or +1. 5/8 is none of those. So that is my real solution. That is not extraneous. That is a real solution that makes sense. Fabulous. Alright, let's do another one. This one does not involve factoring. Lucky for us. I have 2 over 3x plus 1 equals 1 over x minus 6 over 3x plus 1. So what's the LCM here? It's going to be a 3x plus 1 and an x. And that one's also got a 3x plus 1, so that's good. Let's try changing them. So the first term is 2 over 3x plus 1. Multiply that by x over x. That's equal to 1 over x. What's missing is the 3x plus 1 over 3x plus 1. And then in the last one, I don't know why I'm switching colors, minus 6 over 3x plus 1. What's missing is the x part, so x over x. This becomes, let's see, 2x over 3x plus 1 times x is equal to 3x plus 1 minus, over x 3x plus 1 minus 6x over x 3x plus 1. Notice they're all the same now, so if I multiply that to both sides, I'm just left with 2x is equal to 3x plus 1 minus 6x, right? If they're all the same in the denominator, I'm just left with the numerators. And now I have 2x is equal to negative 3x plus 1. Add that to both sides, I get 5x is equal to 1, x is equal to 1/5. Yep. Now, would 1/5 ever yield a 0 here? Well, 1/5 would not be a problem here, but let's double check. Would 3x plus 1 equal 0 if x was equal to 1/5? So let's erase that. Oops. And let's double check. Let's double check that putting a 1/5 here doesn't cause a problem. So 1/5, that would be 3/5 plus 1. 3/5 plus 1, that's going to be 3/5 plus 5/5, that's 8/5. That does not equal 0, so we are good. This is not an extraneous solution, we are fine. Alrighty, we got 1/5. Fabulous. Last but not least, we've got x over 3 plus x over 3 equals 1, a rational equation. Let's see, we can put, so let's do this the same way we did the other ones. Remember, this is just over 1, right? So our LCM is going to be x plus 3 times 1, technically, but we really don't need to put times 1 there. So let's multiply the first term. Well, the first term has everything, so we're good with x plus 3 over x plus 3. Do the other side, get 1 times x plus 3 over x plus 3. Alrighty, and then we get, so let's see, so that's x plus 3 over x plus 3 is equal to x plus 3 over x plus 3. This is looking a little fishy. Multiply, the denominators are the same, so I multiply them to both sides. I get x plus 3 is equal to x plus 3. Subtract, I get 3 is equal to 3. Okay, so my variable has disappeared completely. That is a problem, right? It's not really a problem, actually. It just means that I have an infinite number of solutions. And that makes sense, right? When you look at the problem originally, that idea that something over itself equals 1, that's present throughout this whole thing, right? Otherwise, we couldn't do anything. We can't multiply something over itself if it doesn't equal 1. That would change the equality of the equation. So this is really just sort of explaining that something over itself equals 1. Therefore, no matter what I put in for x, it's going to equal 1, right? Because 5 plus 3 over 5 plus 3 is going to be 8 over 8. That's 1. Negative a million and over negative a million is going to be 1, right? So this is just an infinite number of solutions. Sometimes that happens. Notice you didn't have to identify it right away. You could keep going, get all the way down. If you got something down to 6 equals 3, then you would know it has no solutions. Same thing as way back when we were just solving linears. So all of these bad boys still follow all the rules of algebraic properties. You won't run into these often, but they do happen. They do happen. It's more important to check for those extraneous solutions, though, those ones that don't work. Alrighty, hopefully that answered some of your questions. Otherwise, I will see you in the next video.